So you buy a coffee today for $5. A year later, the same coffee may cost you $5.5. This is inflation. And predicting it helps policymakers control the economy and investors make smart decisions. In this lesson, we will be using publicly available US inflation dataset, which contains monthly US inflation rate over 40 years starting from 1950. As part of this lesson, we will be using ARMA model to do prediction. The focus of this lesson is that we need to apply differencing to make our inflation data stationary, which is a base assumption of ARMA. And then further to that, we will be introducing inverse differencing, which will bring the forecast back to their real world meaning. And finally, we will be evaluating our predictions with key performance metrics, along with the visual comparison of predicted versus actual inflation. So let's get started. Required libraries are already imported, and on loading dataset we see that it has two columns, year month, along with our column of interest, which is inflation_1. Now to have a proper index time series, what we can do, we can combine year month, we can create a new column date, and we can also allocate one day, let's say day 1 to that day to ensure the validity of date. And this we can do with the help of pandas to date time function. As an outcome, we will find this data frame. Now these columns become redundant, and we intend to create date as indexed time series data. So what we can do, we can set index to date and drop the column. As a result, finally we have this data frame in our hand with which we will be proceeding. So this is our target variable inflation, which we need to predict finally. Let's visualize this time series data. So this is a monthly US inflation data. Visually looking at it, we cannot make out whether this series is stationary or not. And so we have in our hand the tool ADF test to check for the stationarity of our. We have already used ADF test earlier. So what I have done, I have created one function with the help of ChatGPT. All we have to do is we have to pass our panda series to this ADF function, and it will give us the p value, and it will give the final verdict whether the series is stationary or not. So let's run this. On running this ADF test, we find that our data is not stationary since p value is greater than 0.05, and what this means effectively is that inflation has a trend or pattern over time. We have to apply differencing technique to make it stationary in nature so that we can further proceed with ARMA modeling, and it removes a long-term trend. So let's say if inflation was 5 last month and 5.5 this month, difference value would be 5.5 minus 5, which is 0.5, and after differencing we will check the stationary again, of course with ADF test, and let's see if it becomes stationary after that or not. So let's create a function to create a difference series, and we can apply it to our original series. Let's name it trend_difference, since with differencing we are detrending the series. And to this function we can pass dataset and interval, which we can assign the default value as 1. So interval refers to the number of lags we are considering. Here in this case we are just creating the difference between current value and previous value. In another case we might need to create further differencing, or let's say in case of seasonality we might need to difference between the current lag and let's say 7-day lag before. So in that case lag interval would be different. So we will run a for loop through the length of the data set, and within this loop we'll create value, which is the difference of data set current value and the value before interval number of steps. I have empty list diff to which I will append this difference value. Finally I'll return the numpy array of this diff list. So this function will help us to create a differenced series. Let's apply this differencing to our current series, which is inflation 1. To this trend_difference we can pass tf, our column inflation_1, we'll fetch the values of it, and our default interval is 1, which means we are subtracting it with previous value. So let's run this. So let's see what this difference series contains. So this is our numpy array of diff values, and you will see that earlier we talked about on differencing we get couple of nan values, but our function is automatically taking care of it by starting our range from first interval, making sure that we do not have any nan value. So now I hope this series get stationary, and let's test it with the ADF test again, and we can pass this difference series to this ADF test, and it gives us a verdict that the series is stationary with p-value 0.0. If we visualize the plot for before and after series, so this is a series which is original and not detrended, and this is the one which we obtained after differencing, and we can clearly see the difference that it becomes more stable. Now we have stationary series in hand, which is the base assumption of ARMA model. We can make predictions on this series, the diff series, rather than the original time series. And let's park this question. Once we make prediction on this diff series, how we can get back to the original time series prediction, because our primary goal is to predict inflation rate and not the difference in the inflation rate. We'll park that for now. This is the length of the original series, and this is the length of the diff series, and we know the difference in the number of record is due to differencing. Further to that, to make predictions, we can split our differenced series into train and test with the help of this piece of code. And when you will run this, you will find that training gets 466, 95% of data, and test gets 24. Further to that, we can try to identify the lag order of the series through ACF and PACF plot, and I have created a function for that, and I have passed different series to that. And this does not make me very clear what is the order. It is quite confusing. I can put it in let's say MA modeling, MA3 order, or I can also have some autoregressive component in it. So what I'll do, I'll just pick 1 3 over here. Okay, and what we can do, we can start modeling. We can apply this model ARMA to this train underscore diff series with the order of 103. 1 stands for P, autoregressive component, 3 stands for Q, MA component, and 0 stands for differencing as 0. Now why the differencing is 0, we have already differenced it 1, and we are only picking difference series and not the original series, and that's what the difference between ARMA and ARMA model is. In ARMA model, we will actually pass the differencing order of the original series, while in ARMA we make the series stationary and then pass 0 over here. Now this is ARMA modeling of train underscore diff, and let's fit the model. Further to that, we can have a look on the summary of the model. We can retrieve the coefficients of AR, only 1 coefficient for autoregressive and 3 coefficients for moving average, and this is the standard. And we can also visualize this model underscore fit through diagnostic method, and we'll see that it's quite a good model. Most of the points are aligning on this red line, and in this correlogram all the points are within this confidence interval, and the data is fluctuating around 0 for this residual. So this seems to be a good model, good fit. So let's first perform rolling forecast or walk forward on difference data, and for that what we can do, we have already learned that in previous lessons. Let's try to do that on your own. All we have to do is we have to create a list of previous training data, initial training data, so which is train underscore diff. We can create an empty list of predictions, and then we can run our for loop to do one step forecasting on test data. We'll loop through the whole test data, and in this case it is test underscore diff, and then we can use the model which we have already decided. Now once we have fitted the model, in each iteration we are fitting it on one value through this walk forward method, and we are fitting it on test diff. So we'll write the predicted as value as y hat underscore diff, and we'll obtain the forecasted value, and then further to that we'll append it in predictions list. And in history we will append the actual test underscore diff value, and let's print it. Let's run this. So once you run this, you will obtain predicted diff values. But this is not what we are looking for. We are not looking for the prediction of diff series. We are looking for the prediction of original series. So what we have to do? When we are doing predictions for diff, we have to do inverse of differencing, right? We have to revert it to original prediction. To do forecast on original series, we will initialize one more variable. You can definitely do it in multiple ways. Inverse transform, this is one way. So we can define one original training data, and we are already defining history with the diff data. We already have predictions in place. So what we can do, we are forecasting y hat underscore diff with the help of a model which we have already freezed. Now this is the difference predicted. Let's say the first difference is predicted between the last value of the training data and the, let's say, some predicted value of test data. To get the predicted value of the test data, we can add the difference to the last value of the trained data, and that will give us the predicted test value. So to obtain the predicted value of test, we can write it as y hat is equal to, we have last value of our trained data plus the difference value. This will give us the predicted test value, and then we can append this predicted value to the predictions list. To have the performance evaluation at later point, we can store actual value as well. Now since we are making predictions on train underscore diff, like in regular walk forward model, we can update the history with the latest value of actual diff value, and further to that we can also update the original history with the original test value. And let's print this, let's run this, and so this gives us the predictions on original scale. Further to this, we can do performance evaluation as well with the key standard metrics, and also we can compare the original data with the predicted data, and this is the graph which we have obtained in our Jupyter notebook. And to have a closer look, we can see that this is the original test data, blue one, and the red one is the predicted data. So this Jupyter notebook is available in resources. So with this we come to an end of this lesson. We were heavily focused on implementing ARMA model with the help of differencing and inverse differencing, all because of the base assumption of stationarity, and this is quite tedious, and as we will move further and we need to use other lags as well, this will become more tedious. So in our next lesson we will be implementing ARMA model on EPS value of Johnson & Johnson, and we'll see with ARMA model we do not need to do any manual differencing and inverse differencing, and the path becomes easy. So I'll see you in next lesson.